Hello. As I said at the end of the last video, we are going to consider the most general simultaneous equations model. Actually, not most, just like among linear models, this is the most general. So we assume that there are k different endogenous variables. So I will use the capital letter to denote the vector, and scalar variables are lowercase letters, and there are m exogenous variables similarly defined. And then we will assume that all variables have mean zero to ignore the intercept. And then the structural equations, must be composed of k equations. If the number of equations is smaller than k, that means some endogenous variables are not determined. So, like, say, two equations cannot have a unique equilibrium for three variables. So, and there must be at least the same number of equations, at least the same or greater number of equations than the number of endogenous variables for the endogenous variables to be well defined, uniquely defined. And if the number of equations is greater, there is another problem. There is an over-identification problem, which is not a problem. You may utilize the extra information for testing or for estimation, but we are not going to consider that because if there are more equations than the endogenous variables, it may be possible that there is no solutions, no equilibriums, like the generalized method moment problem. So it complicates the analysis. So we are going to rule out this case either. Therefore, simply we are assuming that there are k equations so that the endogenous variables are there is a unique equilibrium for the endogenous variables. Of course, we are going to assume the basic assumptions that the equilibrium is unique, exists and unique. Like gamma 1, gamma 2 is different from 1. So that was assumed. Then in this setup, this is our model, the most general model. I allow everything depends on everything else. So first equation has uh, k different endogenous variables and m different exogenous variables and an error term. So each equation has all endogenous variables on the left hand side, all exogenous variables on the right hand side, and then error term at the end of the right hand side. This is the general structural form, and the kth equation, say kth equation like this one line, can be summarized in this way: vector y times vector of coefficients gamma k and xi vector xi times the vector of beta k plus epsilon. This is the kth equation, and then combining all of them, you may write it this way. So this is the most general form of the simultaneous equations. Everything is vector or matrix, and check the dimension. Then, so okay, this is the structural form. You may impose some restrictions on there, but like without the restrictions, let's see what we can do. And first, as I said, we need to assume that the equilibrium is unique, which means that this matrix must be non-singular. It must be invariable. So that y defined in this way is unique. So y is given, the equilibrium y is given by gamma inverse beta x plus gamma inverse epsilon. So this is pi, the reduced form parameters. and this is the, excuse me, reduced form error term. So in the simpler model, you can match what is what. So pi11, pi12 guys are, those coefficients are in here, and the error term also looks more complicated because it's defined it this way. And obviously pi is a matrix, and if u is also a vector, so everything is matrix or vector. And then this reduced form equation has no problem. It satisfies the classical linear regression assumptions as long as this is satisfied and this is satisfied, which we will maintain throughout this analysis. So it's obvious. So exogeneity, because X is exogenous, full rank is a separate assumption. Of course, it is mild. We have to have this. Then, okay, pi is identified. Under these assumptions, pi is identified by the classical linear regression method. Then, how then we know pi? Then how do we identify the underlying structural parameters gamma and beta? And then clearly you see the different dimensions. Pi is k by m dimensions, but gamma is k by k, beta is k by m. Absolutely, this is more than what you have. So there are more unknowns than the information you have. So pi may be enough for beta only, but gamma is just extra. It's you cannot identify all of them. So we need additional assumptions. This is similar to the case where this. So this is in 2x2 cases. This is the general assumption, general model, but still it has an assumption. First, coefficient of this is 1, coefficient of this is 1. So we already have two restrictions. Still it is not identified. Earlier also to identify this, we have to have two restrictions plus this and this. So this must be excluded, this must be excluded. So these four restrictions will identify all the parameters. That was the intuition we used in the simpler model. So now we are going to consider what kind of assumptions we need in a general setup. So we need similar assumptions. So, and we are going to consider equation by equation. So let's think about the kth equation. Kth equation can be written in this way. So, like gamma k, pi, and beta k. So this is the relationship between the reduced form parameter and structural parameter in the kth equation. By the way, I am not using inverse because pi is not invertible. Pi is not a square matrix, so we cannot use inverse here. And this is one information we have, like not one, but it's this is what the reduced form gives you, and the restrictions will be written in this way. I'm going to write the restriction this way. So it is a matrix and it is another matrix. So the restrictions are denoted this way, and I use minus here for simplicity. Later you will see why, like just to match the sign between this and this. Then, so you may consider these examples, like say normalization. As I said, one of the coefficient in each equation can be normalized to 1, right? Otherwise, you can multiply a constant to every term without changing the equation. And second, exclusion restriction. This is exactly what we did to identify the model in model 4. So some of the gamma coefficients are 0. That is exclusion. Some of the beta or gamma are 0. And you may simply assume that some parameters are known, like this, or linear relationship between the parameters, something like this. Say two parameters must be summed to 1, or the two parameters equal to each other. These kind of assumptions are coming from economic theory, for example. So if you go back even more, say think about the macro model. In the equilibrium equation, so there are three equations. Three equations determine consumption, investment, and income. But it is obvious that the income equals to consumption plus investment plus government. So the coefficients are automatically 1. So it is obvious in this case, like obvious from economic theory. So that becomes an additional restriction you can use in your estimation. And also, we assume that interest rate does not affect, say, the consumption, for example. So, and in this example, Gruner-Duopoly model, the demand function and the two firms' best response functions determine price and each firm's outputs. So three variables are determined by three equations. Here you may utilize that the two firms are symmetric. So the coefficient of this equals to this, and this equals to this. So in that way, we may find some also coefficient in front of Q1 and Q2 are the same. So these are the restrictions you may use in this analysis. So they are, excuse me, they are examples of these kind of restrictions. So you can imagine them. And if you want, it would be a nice exercise if you can write the example equations into a matrix form. Write the general matrix and represent the restrictions as a matrix form. That would be a nice exercise. So we have two equations from the restrictions and from the general structural model. Then we have this, and here this is only about kth equation. So we would like to identify this. Then its identification depends on the invariability of this. So if you can invert this matrix, then you can identify this. So that is as simple as this. So you have to have rank. If you write this matrix as A, its rank must be n-list the number of these parameters, the dimension of the parameters, k plus m. Then you can identify. So then, in summary, usually it's there are two common names for the condition. First, a necessary condition, which is usually referred to as the order condition, which means there must be n-list as many restrictions as the number of endogenous variables. But so it is like we have 5 unknowns, but we have 3 informations. Then you cannot identify because it's not enough. This violates, in this case, the order condition is violated. The number do not match. This part, the number of informations must be n-list equal to the number of unknowns. If that does not work, then order condition is violated. However, even if the numbers are the same, as we see in model 4a, even if the numbers are the same, still it does not guarantee identification. So, because some of the informations may be duplicate, so you have to check the rank. The rank must be the rank of not only the number of informations, but but the rank of the information should be should equal to the number of unknowns. This is the sufficient condition for identification, and that is called rank condition. So just simply counting the number, it's simple, but it does not guarantee to check exactly if you want to claim that the parameters are identified, then you have to show that the rank is as many as the number of parameters. That's the general argument in this model. Okay, I will talk about the estimation very briefly in the next video. Bye.